Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to look at how artificial intelligence shifted from symbolic approaches based on rules and logic to machine learning systems that learn patterns from data.
It's a magnificent journey, honestly. And it's not just a technological pivot,
No, not at all.
We are basically tracing this fundamental philosophical argument about what intelligence even is. It's the old conflict between rationalism and empiricism, but it's playing out in, silicon and software.
That's such a great way to put it. Historically, AI research was really dominated by two fundamentally opposing schools of thought. On one side, you had symbolism,
Right.
which claimed intelligence was all about manipulating these abstract, predefined concepts. And on the other, you had connectionism.
Connectionism,
Yeah.
which argued that intelligence just sort of emerges. It emerges from statistical learning, from patterns you find in massive amounts of data.
So our mission today is to really understand that whole arc.
We need to grasp what each of these paradigms prioritized. Why connectionism, which rapidly evolved into what we now just call machine learning or ML, why that became the dominant force, and crucially, why we're now seeing this inevitable synthesis.
The combination of the two.
Exactly. The future of AI, the kind of AI that's truly cognitively powerful, it seems to lie in combining them into what researchers are calling neural symbolic computing, or NESI.
So let's start where it all began, the era of thinking machines that were built on pure, unadulterated logic.
The age of symbols.
When AI first emerged back in the 1950s, the mood was incredibly optimistic. The foundational idea, what they called the symbolic conjecture, was based on this premise that human intelligence uses symbols.
Right. Discrete units.
Yeah, discrete units representing objects, ideas, relations. Those were seen as the basic building blocks of thought.
And if you accept that premise, then intelligence becomes this top-down affair. The whole cognitive process is just achieved by manipulating these symbols through a predefined library of rules, logic operations. It's the hallmark of that rationalist strategy. You define all the knowledge you need explicitly right at the start, and then the machine just reasons with it.
It sounds almost mathematical, like geometry. You start with a set of axioms and you just derive all the possible theorems from there.
Precisely. That's a perfect analogy. It aligns perfectly with the rationalist school of mind, which prioritizes knowledge that's acquired through, say, evolution or explicit development, totally independent of raw sensory input. You didn't need a lot of data.
Yeah.
You needed a lot of very smart people to sit down and program the knowledge.
Which I imagine was a huge advantage in the 70s and 80s when data was incredibly scarce and computers were, ridiculously slow. They relied on expert knowledge.
That's the key. Symbolic systems run on prior explicit knowledge and inferencing. They use these incredibly structured and powerful declarative languages like first-order logic or propositional logic for their knowledge representation.
And when they worked?
Oh, when they worked, they had a virtue that we desperately, desperately crave in modern AI interpretability.
The famous white box advantage.
Yes. Since every single decision was just a logical step derived from a known human-readable rule, the system could literally print out the entire sequence of steps it took to reach a conclusion.
You could plop the hood.
You could open the hood and see this flawless step-by-step reasoning process. If the AI concluded, say, that X is true, it could show you the rules and facts it used.
Yeah.
A and B implies X. Transparency was built right into the architecture.
So if they were so transparent and so logically sound, why did the symbolic paradigm ultimately, struggle to survive in the real world?
Because the real world is.
Yeah.
It's incredibly messy, it's ambiguous, and it completely defies neat categorization. The limitations were, I'd say, threefold. First, the sheer effort required for hand-tuning was astronomical. Every rule, every single relationship had to be manually defined by domain experts. This meant they lacked any true capability for genuine learning or, adapting outside of those predefined human-imposed boundaries.
And I guess that leads directly to the famous brittleness issue.
It does. Can you give us a quick real-world example of where that failure, that lack of ambiguity tolerance really hurts?
Sure. I mean, Think about something as simple as visual recognition. If a symbolic AI is programmed with the rule, a chair has 4 legs, a seat, and a back.
Okay.
If you show it a photo of a chair that's partially obscured, or maybe a stool with only 3 legs, or a modern designer chair with a totally non-traditional back, the system just fails completely.
It breaks.
Its discrete, handcrafted rules are just intolerant of the noise and the ambiguity that's inherent in real-world data.
And that inability to deal with ambiguity led to the second massive problem,
Right.
scaling. The complexity of trying to map the entire real world, its infinite combinations of objects and contexts and actions into an exhaustive set of logical rules just became an impossible task. They struggled massively when dealing with complex real-world problems like image recognition where, slight change in the light or the angle just ruins the input.
So the systems would just seize up.
They'd seize up and fail to scale.
So the symbolic approach was great for these tightly controlled, discrete problems, proving mathematical theorems or playing chess on a grid.
Perfect for that.
But it just collapsed when it was faced with the chaos of reality.
And that spectacular failure, the brittleness and the scaling issues, that really set the stage for the opposition, the connectionist counter-revolution. This school just flipped the rationalist assumption on its head and embraced the empiricist view.
So instead of assuming intelligence stems from predefined symbols, connectionism postulated that intelligence arises from learning associations directly from, sensory input and data. It's the ultimate empiricist view of the mind.
The conceptual roots go all the way back to formal neuron concepts, like the model from McCulloch and Pitts. But the revolution, it really took off when this idea was formalized into what we call machine learning.
Okay, let's unpack this. We hear machine learning everywhere. For an audience that knows the topic, what does ML fundamentally mean beyond just, improving performance? How does it differ conceptually from symbolic AI?
It's fundamentally defined by its commitment to discovering statistical structures, patterns that are just, they're too complex, too nuanced, or maybe too ambiguous for human experts to sit down and explicitly encode as rules. A system has learned if its ability to perform a task measurably improves as it gains more experience executing that task.
The commitment is to experience.
Exactly. Let's go back to your cancer detection example. A symbolic AI would need rules, right? If the report contains descriptor X and D marker Y, then output cancer. The connectionist ML system, it doesn't get rules. Its raw experience is millions of patient reports. Its measurable performance is the accuracy of its prediction, which gets validated by oncologists. As it analyzes more and more reports, it discovers these subtle statistical correlations, these patterns, that link combinations of symptoms or measurements to the outcome, patterns no human might have ever defined.
So the conceptual shift is away from rule-based methods where every single path is programmed, and it's toward data-driven methods that learn statistical patterns from examples.
It's a complete paradigm shift. And the critical factor for its dominance was the explosion of 2 key resources. Massive data sets, that's the experience, and vast compute power, which is the ability to process all that experience.
Right.
Since the turn of the century, this connectionist approach just became the dominant paradigm in both AI research and commercial applications.
And I think its robustness against noisy data is what truly separates it from its symbolic predecessor. If the input is a little bit smudged, the ML system might just lower its confidence score a bit.
But it doesn't break.
But it rarely fails catastrophically like the symbolic systems did.
That robustness is so key. I mean, look at the applications. They are vast because they solve problems where the rules are either unknowable or just way too complex to write down. Online services like product recommendations, fraud prediction, natural language processing, robotics.
All of it.
All these domains are dominated by ML because they excel at recognizing patterns and making predictions in the face of statistical uncertainty.
Okay, so since ML is really the backbone of modern AI, we should probably get into the nuts and bolts. When a machine is learning, what types of problems is it tackling, and what methods does it use?
Well, we typically group ML problems into 3 categories. You have classification, regression, and clustering. Now, classification and regression are usually handled by what we call supervised learning.
Which means the machine trains on labeled data.
Exactly. Input variables linked to known answers. Clustering, on the other hand, is unsupervised learning. It deals with unlabeled data, trying to find some hidden structure. We also have things like semi-supervised and reinforcement learning, but supervised learning gives us the clearest look at the core mechanics.
Okay, let's start with regression then, which deals with continuous variables.
Regression models are all about forecasting a continuous numerical output. This could be anything from predicting real estate prices to forecasting next quarter's sales figures or trying to model stock market movements.
The simplest starting point for that is linear regression. It just tries to fit a straight line to the data.
It does.
Yeah.
It assumes a linear relationship exists between the input and the output. Its strength is its sheer simplicity. It's computationally efficient, easy to interpret. You know exactly how much each variable is contributing.
Right.
It's also less prone to overfitting if you use proper regularization. But, as you said earlier, its major weakness is that it radically oversimplifies most real-world problems.
Yeah.
They're rarely purely linear.
And when you're dealing with that real-world complexity, you move to multivariate regression.
Precisely. If you're trying to predict the value of a house, you can't just use square footage. You have to factor in the number of rooms, the neighborhood quality, distance to schools, crime rates.
A whole host of things.
The dependent variable relies on multiple independent factors, and this gives us much, much deeper predictive insight into complex phenomena.
But I imagine this multivariate complexity comes with some practical hurdles.
It absolutely does. It's statistically challenging. The model needs specialized expertise to set up correctly. And most importantly, to achieve high statistical confidence in your findings, you need a huge volume of input data. A large sample size is critical to properly capture the variance from all those independent factors without, concluding that a spurious correlation is actually meaningful.
So moving from those continuous numerical outcomes to discrete outcomes, that brings us to classification.
Classification is all about predicting a categorical outcome. Is this email spam or not spam? Is this tumor, malignant, or benign? Which type of cuisine will this user prefer?
And logistic regression is the baseline algorithm here, right? Highly used in industry.
It is the workhorse. Logistic regression predicts the probability of an event occurring 0 or 1 or multinomial outcomes.
Huh.
It's computationally efficient. It scales really well for massive industry problems. But like its linear cousin, it struggled immensely with nonlinear problems because its decision boundary, the line it draws to separate the classes, is linear.
Okay, so if the classes are all mixed up, like scattered dots that can't be separated by a simple straight line, where does the machine go for more sophisticated pattern recognition?
You move to algorithms that are designed for nonlinearity, like the support vector machine, or SVM.
Okay.
The core mechanism there is defining a hyperplane that acts as the optimal decision boundary, separating the classes in the data space.
So what makes an SVM good for those complex, messy, nonlinear problems that logistic regression just couldn't touch?
This is where the core insight, what they call the kernel trick, comes in. Imagine your data points, the blue dots and the red dots, are completely intertwined on a flat table. You can't draw a line to separate them.
Right.
The genius of SVMs is that you can stop fighting the nonlinearity by mathematically transforming the problem into a new dimension where a simple line will work.
So you're basically folding the data space.
Exactly. Using these complex mathematical functions called kernels, the SVM maps the data into a higher dimensional space. It's like lifting the tablecloth. So the points that they're all intertwined on the flat surface are now clearly separated in 3D or 4D space.
And then it draws the line.
Once they're separated in that high-dimensional space, the SVM draws the optimal linear hyperplane, and then it projects that boundary back down to the original space. It handles high-dimensional data really well and is generally less prone to overfitting because it's focused on margin maximization.
That's a fascinating insight. If you can't solve it simply, you make the problem space more complicated until the solution becomes simple again. What are the downsides of SVM?
Well, its performance degrades pretty significantly with very large data sets. The training time increases exponentially with the sample size. And, unlike simpler models, trying to interpret why the SVM chose a certain boundary based on some complex kernel function can be really difficult.
We also often see decision trees used in these complex scenarios.
Right. Decision trees solve problems by continuously asking binary questions, splitting the data based on parameters until a final decision is reached at a leaf. Their massive advantage is just sheer interpretability. They're highly transparent about the decision path, and they handle mixed data types, categorical, numerical, very well.
But they have issues too.
Oh yeah. A single decision tree is unstable and really prone to overfitting, which is why in practice, people almost always use ensemble methods like random forest or gradient boosting machines to stabilize the outcomes.
Okay, so that covers the structural ways we map data, whether we use a line, a folded hyperplane, or a tree structure. But regardless of which model we choose, the central question is still there. How does the system, without any human help, actually move from a terrible prediction to an accurate one? That's where the process of optimization comes in.
Indeed. We're moving from the model types to the engine of learning, which is primarily driven by gradient descent and backpropagation.
Let's break down gradient descent first.
So gradient descent is an iterative method. It has one singular objective: to minimize a cost function. The cost function is just a measure of the error, how wrong the model is. To minimize it, the algorithm has to find the point where that error is lowest, what's often called the local minima.
So if the hill represents the error landscape, is the gradient just the mathematical way of calculating which direction is steepest?
That's the perfect analogy. You're standing on a hill in a dense fog. You can't see the whole valley, but you can feel the slope immediately under your feet. The algorithm repeatedly computes the gradient, the partial derivative or slope of the function, which tells it which direction is the steepest downward path. And then it takes a step in that direction.
And the size of that step is dictated by the learning rate.
The learning rate is so critical, and it presents this terrifying balancing act in practice.
Right.
If the learning rate is too fast, the algorithm takes these huge steps and it can just overshoot or bounce over the lowest point in the valley completely. If it's too slow, it might take a million tiny steps and take forever to converge. Best practice often involves these sophisticated schedules where the learning rate starts fast and then gradually slows down as the error gets closer to its minimum.
We mentioned there are variants of this depending on how much data is processed per step. Can you detail the practical trade-offs of the three main types?
Absolutely. The variants are all about trading stability and memory for update frequency. First, you have batch gradient descent, or BGD.
Okay.
This computes the error across the entire data set before it updates the model's coefficients. It offers great stability because the update is based on the true gradient of the whole loss function. The downside: it's computationally slow for massive data sets and requires the whole data set to be held in memory.
Then the opposite end of the spectrum.
That would be stochastic gradient descent, SGD. This is the extreme opposite. It updates the parameters for every single training example.
Wow.
It's incredibly fast to update, and it can be robust because the frequent updates might jiggle it out of a bad local minimum. However, it introduces really noisy gradients. The error rate jumps around wildly, which makes the convergence less smooth.
And the middle ground.
Mini-batch gradient descent, or MBGD. This is the practical champion, especially for deep learning. It splits the training data into small, manageable batches, say 32 or 64 examples, and performs an update for each batch. This is the sweet spot. It gets the computational efficiency you need for huge modern neural networks while maintaining enough stability to ensure a relatively smooth convergence path.
So MBGD is the engine that drives most of the modern neural networks we hear about today. And when we talk about training those complex, multi-layered networks specifically, we introduce backpropagation.
Backpropagation, or backprop, is just the efficient algorithm used to calculate and apply those gradients within a neural network. It takes the calculated error from the final output layer and it propagates it backward through all the hidden layers. It uses the chain rule from calculus to efficiently figure out how much each individual weight in every single neuron contributed to the final error.
Which lets it adjust those weights precisely.
Precisely. Without backprop, deep learning networks would be computationally infeasible to train.
But the very complexity that backprop enables, the vast number of hidden units and simultaneous weight adjustments, brings us right back to the inherent drawback of the connectionist system, the black box problem.
It's amazing, but it's also terrifying, isn't it? Neural networks are essential when you have no well-defined rules, but because of the complexity, the system is learning millions of statistical correlations at the same time, it becomes nearly impossible to explain how the solution was arrived at. We have these powerful systems driving cars, recommending medical treatments, and sometimes the best answer we can give is, well, the math worked out. The process is totally opaque.
And training itself is just fraught with practical challenges beyond just choosing the right learning rate.
Absolutely. Training time can be extremely long, and it demands huge sample sets. Furthermore, backpropagation can run into specific issues. There's the moving target problem, where the optimization objective is constantly changing, making it hard to settle on a solution. You can also get network paralysis, where weights become too large and units get forced into regions where the activation function's derivative is basically zero, which just halts learning.
And the risk of getting stuck.
And of course, the perpetual risk of getting stuck in a local minimum instead of the desired global minimum.
So we've really reached a clear philosophical and technical divergence here. Symbolic AI was great for explicit reasoning and transparency, but it was brittle and couldn't learn from messy data.
Right.
And connectionist AI is excellent at learning and perception. It's robust against noise, but it's terrible at explaining itself or performing complex compositional reasoning.
For many years, the technological success of connectionism just overshadowed everything else, and a lot of people claimed symbolic AI was obsolete. But true human-like intelligence, it can't be achieved by pure statistical correlation alone. Pure connectionism has these critical, undeniable limitations.
So what are the fundamental deficiencies of a pure neural system that forced researchers to look back at symbolic structures?
Simply put, pure neural systems are superior in perception intelligence, image recognition, speech processing, dealing with unstructured data. They learn patterns brilliantly. However, they critically lack effective reasoning and high-level cognitive ability.
Right.
They also exhibit poor generalization. If they see a novel situation that wasn't statistically represented in their training data, they often fail spectacularly.
Yeah.
And their black box nature makes them totally unsuitable for domains that require legal or safety guarantees.
And the symbolic systems are the mirror image. Strong reasoning, perfect interpretability.
But poor perception and learning ability, they are profoundly complementary. If we want an AI to not only recognize 1,000 objects in a photo, that's perception, but then deduce, based on logic, complex relationships between those objects and predict future states, that's reasoning. We need both working in concert.
The philosophical tension that underpins this necessity, it really comes down to the central paradox of cognition, which was highlighted by researchers like Paul Smolensky.
Yes, this paradox exists between compositionality and continuity.
Yeah.
Human thought relies on compositionality.
Okay, what's that?
It's the idea that complex information like understanding the sentence, "the cat is chasing the ball," is systematically and recursively built from smaller, discrete structures. This is formalized perfectly in discrete symbolic computing.
Yeah, the physical brain.
The physical brain operates via continuity. Information is encoded by these continuously varying numerical activation levels of billions of neurons. Neural networks embody this continuity, so the brain is simultaneously a continuous statistical machine and a discrete rule-based machine.
So to achieve true cognitive intelligence, you can't have one without the other. You need a system that addresses both principles at the same time.
This is exactly why the dual process theory of the mind is so relevant to AI research today, cited by Daniel Kahneman and AI pioneers like Yoshua Bengio. This theory posits two distinct cognitive systems in the brain.
System 1 and System 2.
System 1 is intuitive, rapid, unconscious pattern matching. That's the neural network side. System 2 is deliberative, logical, sequential, conscious, and reasoning related. That's the symbolic system side.
Therefore, the goal of neural symbolic computing, or NESI, is to unify these two systems in code. We're aiming to build an AI that can seamlessly transition between System 1 perception and System 2 logical reasoning.
It's the necessary third wave of AI research. We're trying to create a hybrid system that is both robust and explainable, capable of perception and logical deduction.
That sounds incredibly ambitious. How are researchers actually gluing these two radically different paradigms, the continuous and the discrete, together?
The foundational goal is to find a function, call it F, that can successfully map both continuous data, X, and discrete symbols, S, to the final ground truth output, Y. Researchers have developed a pretty robust taxonomy to categorize the various methods of fusion based on the direction of information flow. We generally see three main integration methodologies.
The first one is called learning for reasoning, or serialization. This is where the neural network output feeds sequentially into the symbolic system.
Correct. The goal here is to use the massive computational power and pattern recognition of NNs to enhance the capabilities of symbolic systems. The NN acts in one of two ways, as an accelerator or as a transformer.
So how does the NN serve as an accelerator for reasoning?
Well, symbolic reasoning, especially on large structures like knowledge graphs, often involves a search process across a massive, computationally expensive space. NNs are employed to reduce that search space. For instance, models like PlogicNet or ExpressGNN use graph neural networks to replace traditional heuristic algorithms, rapidly identifying the most promising paths or rules, and thereby accelerating the complex symbolic inference process without changing the underlying logic itself.
And the second role, the transformer or abstraction layer.
This leverages the NN's core strength, extracting structure from chaos. The NN abstracts or translates or extracts clean, discrete symbols from messy, raw, unstructured data images, text, speech to provide meaningful inputs for the symbolic system. A perfect example is the Neurosymbolic Concept Learner, or NSCL.
Okay.
It takes visual input and natural language commands, and its neural component identifies concepts like red, cube, left of, and outputs those as structured symbols. This allows the symbolic component to perform highly complex reasoning like, is the object left of the red sphere also metallic?
So moving on, the second category is reasoning for learning, or parallelization. This is where symbolic knowledge guides the neural network training.
This is vital for combating that black box problem. The NN is still doing the data-driven learning, but we inject human knowledge logic rules into the training process to constrain it. We use that symbolic knowledge to enhance performance, improve generalization, and force the network to respect explicit rules.
So the symbolic rules are encoded as boundaries for the neural system.
Exactly. The systems operate in parallel during the training phase. The symbolic knowledge is encoded into a mathematically suitable format, often as a regularization term or a penalty, ensuring the network's internal statistical correlations adhere to known facts. Things like, a person cannot be both male and female simultaneously. We can get into the mechanics of this integration more.
And finally, the third category is learning reasoning or interaction, where there's a constant bidirectional exchange.
This is the unified ideal. It aims for iterative refinement, where both paradigms play an equal, mutually beneficial role. The NN output feeds the symbolic component, and the symbolic component's output feeds back to refine the NN's learning. This iterative loop is crucial for deep end-to-end learning across that continuous discrete divide.
What's a leading example of this sophisticated bidirectional exchange?
Deep Problem is a seminal example. It seamlessly integrates a continuous neural network with a discrete logic programming language. It uses NNs as neural predicates.
What is a neural predicate?
It's a fact whose probability of being true is calculated by the neural network based on unstructured data input. So, for example, if you input an image of a cat, the NN calculates the probability that the predicate is the cat image is true. This probabilistic fact is then fed into the symbolic reasoning component, which uses a logic programming language to answer complex logical queries like, is the animal rideable or not? The system is trainable end-to-end because the continuous probability calculation by the NN and the discrete reasoning by the logic system are bridged using gradient-based optimization tools.
Let's focus intensely on reasoning for learning. This feels like the most direct path to making our black box neural networks accountable to explicit human knowledge. How precisely do we translate a logical rule, a human constraint, into a training restriction that a continuous optimization algorithm like gradient descent can actually process?
Right. This category is divided into two primary technical strategies: regularization models and knowledge transfer models.
Starting with regularization models, which essentially add penalties to the loss function.
The core mechanism is integrating symbolic knowledge by adding regular terms to the model's objective function. Every time the model's prediction violates a known logical rule, that regular term imposes a mathematical penalty. This forces the optimization process to move the network weights toward solutions that adhere to the logic.
We mentioned semantic loss or semantic-based regularization. How does it achieve that mathematical conversion?
SBR and semantic loss are powerful because they encode a high-level logic formula propositional or first-order logic into a real-value differentiable function that the NN's gradient can actually process. This is the critical part. Discrete logic, true-false, cannot be optimized by continuous gradient descent.
So how do they bridge that gap?
Semantic loss specifically uses sophisticated arithmetic circuits, often a sentential decision diagram, or SDD. The SDD is necessary because it takes that messy, high-level logical rule, the human constraint, and converts it into a mathematically smooth, differentiable function that the neural network's backpropagation can actually use. It transforms the discrete logic constraint into a continuous penalty term in the loss function.
That's the real technical challenge, making logic flow backward through the network. Give us a detailed example of this constraint in action, like the Lennon SR model.
Okay, consider relationship detection in images. We have prior knowledge, a rule. If P is true, then Q must also be true.
P implies Q.
Exactly. P could be the fact person is wearing glasses, and Q is the fact glasses are on the person's face.
Yeah.
LenSR works by taking this logical constraint, expressing it as a graph, and then using a graph neural network to learn a robust vector embedding of that logical knowledge.
And then
The system designs a loss function that requires the probability distribution predicted by the main neural network to align with the embedding of that logical knowledge. So if the NN predicts a high probability for P, wearing glasses, but a low probability for Q, glasses being on the face, the loss function imposes a hefty penalty derived from that P, implies Q constraint. This forces the network to adjust its weights until its output probabilities respect the human-provided logical rule.
That is a very sophisticated way of preventing the black box from learning outcomes that are statistically correct, but logically impossible.
Precisely. It brings accountability to the statistical prediction.
Moving to the second strategy within reasoning for learning, knowledge transfer models. These often leverage knowledge graphs.
Knowledge transfer is incredibly valuable in situations where data is severely limited, like in zero-shot learning, or ZSL. ZSL requires the model to identify an object it has never seen before visually. How can it do this? By using knowledge graphs as a semantic bridge.
So how does the knowledge graph substitute for missing visual data?
The KG provides the necessary semantic knowledge. It defines the properties and relationships of all possible classes. So when the model sees an unseen class, let's say a giraffe, it hasn't seen an image of it, but the KG tells it that a giraffe has a long neck, spots, and hooves. The process transfers this abstract knowledge from the semantic domain, the KG, to the visual domain, the NN.
Can you walk us through the mechanics of a model like SEKB, ZSL, or DGP?
Sure. In these models, a convolutional neural network, a CNN, extracts the visual features from the input image. Simultaneously, a graph neural network learns the feature embeddings of the nodes within the KG's semantic space. This GNN builds a set of semantic classifier weights, essentially telling the system what the features should be based on logic and relationships.
So the symbolic structure defines the visual expectation.
Exactly. These semantic weights, derived purely from the structure of the KG, are then used to supervise the training of the visual classifier weights. The visual network is essentially being taught, look, a giraffe should have properties X, Y, and Z, so learn to associate those properties visually. This lets it classify a new object based on those properties, even if it hasn't seen that specific object's image during training.
I recall DGP specifically improved on this by addressing an issue called oversmoothing. What does that mean in the context of a knowledge graph?
Oversmoothing is a common failure in GNNs, where after too many propagation steps, the node features become indistinguishable from their neighbors. The graph essentially becomes a smooth, featureless blob. DGP introduced an attention mechanism to calculate specific connection weights between nodes in the KG. This enhanced the semantic fidelity and prevented the loss of subtle, crucial distinctions between categories, ensuring the transferred knowledge was accurate and precise.
And this approach isn't just limited to recognizing new objects, it's also used in few-shot classification, where you only have tiny amounts of data.
Yes. Models like KGTN use knowledge graphs to capture deep correlations between seen and unseen classes. For example, if you know how cat relates to lion, they're both felines, you can use that learned correlation structure to quickly generalize from one to the other. KGTN employs a gated graph neural network to learn that graph node embedding. This rich embedding, capturing complex correlations, generates the final weight structure for the prediction module, allowing the network to make high-confidence predictions with minimal visual examples.
It's clear that NESI is no longer just theoretical. It's solving real high-impact problems. Where are we seeing the most pronounced advantages of this fusion, particularly concerning interpretability?
The most natural and compelling area is intelligent question answering, or QA, and vision language reasoning. Simple QA can be solved statistically, but complex QA requires logical deduction, making it an ideal fit for NESI.
How do these hybrid systems tackle complex questions?
They use a technique called semantic parsing to translate natural language questions like, what color is the cube left of the red sphere, into an executable symbolic program or logic form. The classic implementation involves neural module networks, or NMNs. The system interprets the question as a sequential program composed of specialized, learnable neural modules.
So the question, what color is the cube left of the red sphere, gets translated into a sequence of steps like find the red sphere, then attend to the area left of the sphere, then recognize the cube, and finally classify its color.
Exactly. Each step is an atomic reasoning operation. And the massive benefit is that because the system generates that expressive logic form, that sequence of steps, you have a fully traceable reasoning process. This is the interpretability holy grail. You can debug the AI's logic if it makes a mistake, unlike a pure neural model which just outputs a probability score.
What about physical embodied systems like robotics and control?
NISI provides a powerful solution for autonomous systems by mirroring that System 1, System 2 split hierarchically. Decision-making gets decomposed into two layers. The high-level symbolic planner defines what to do, the overall logical task plan. This explicit plan then guides the low-level reinforcement learning component, which determines how to do it, the precise motor controls needed to execute the plan.
This sounds like it significantly improves safety and efficiency.
It does. The low-level learning is constrained by the logical high-level plan, leading to improved safety and drastically better data efficiency. The agent doesn't have to statistically learn that driving off a cliff is a bad idea if the high-level symbolic map already contains the rule, avoid cliffs.
We also see major gains in purely abstract, reasoning-heavy tasks like mathematical reasoning.
Solving math word problems requires linking language comprehension with formal symbolic manipulation rules. Purely neural models often struggle with the compositional nature of mathematics. NISI solvers generally outperform them by using tree-structured decoders. These decoders explicitly explore the abstract syntax tree of mathematical expressions, ensuring the final generated equation is both syntactically sound and logically consistent with the language input.
And finally, in visual scene understanding, how do we use external symbolic knowledge to improve how the machine perceives structure?
This is a direct application of that reasoning for learning concept, but focused on visual composition. Models incorporate external symbolic knowledge like rules formalized in first-order logic, such as a car has four wheels or glasses are part of a person, directly into the network training. This formalized logic is converted into differentiable objectives.
Like in LogicSeg for semantic segmentation.
Yes. By adding this rule, the system is forced to be accountable to a human-readable constraint. This boosts the network's training by forcing it to respect known compositional relations between objects in a scene. The resulting segmentation is not just accurate, it's also plausible and logically consistent with the world model embedded in the symbolic rule set.
That covers the current success stories. But if NESI is truly the future, we have to look honestly at the three major research challenges that still stand in the way of realizing its full potential.
The challenges are significant, and they relate directly back to the inherent technical weaknesses of the foundational symbolic systems, primarily their computational intractability and reliance on manual input.
So, challenge number one, the need for more efficient methods.
Right. Symbolic reasoning often involves computationally intractable, precise inference. Think about complex rule sets like Markov logic networks. The number of logical groundings, the instances where rules apply can increase exponentially. We have to accelerate these processes. Researchers are actively working to leverage the computational strengths of NNs to dramatically reduce the search space in symbolic problems, providing neural speed for logical tasks without sacrificing the required logical accuracy.
The second major hurdle deals with the input itself, the automatic construction of symbolic knowledge.
This is a huge bottleneck. Currently, constructing detailed logic rules, knowledge graphs, and precise prior knowledge relies heavily on time-consuming, laborious manual efforts from domain experts. If AI is going to scale, it cannot rely on manual data entry. A core research imperative is enabling end-to-end learning systems to automatically acquire or induce logic rules and prior knowledge directly from unstructured data.
Minimizing the human in the loop.
Exactly. And the final hurdle relates to the symbols themselves and how they're represented. Challenge number 3 is achieving robust symbolic representation learning. Current methods struggle when predicates have similar semantics but different logical formulas. For example, distinguishing the subtle logical differences between next to and near in a visual scene.
They're semantically close.
Very close, but logically distinct in terms of constraints. Designing methods to capture this precise semantic information, potentially using sophisticated heterogeneous graph representation learning, is crucial for refining the nuanced reasoning capability of NASI models. We need to ensure the machine understands the subtle differences between similar concepts and applies the correct logical constraints based on that nuance.
This has been a truly comprehensive exploration. We started with the rigid logic systems of early AI, driven by the belief that intelligence is derived entirely from rules. We saw how that paradigm fractured under the weight of real-world ambiguity, giving way to the adaptive power of modern machine learning, which learns from pure data and statistics.
And now we see the necessary sophisticated fusion. The philosophical debate between the rationalists and the empiricists is being settled in the architecture of NESI. This movement isn't just a technical fix. It is driven by the fundamental necessity to combine learning, System 1, with reasoning, System 2. We're aiming for an AI that is not only powerful, robust, and generalizable, but also transparent, explainable, and capable of human-like cognitive leaps and compositional thinking.
The future is hybrid. If we successfully bridge this divide, what new classes of complex problems, previously inaccessible to either pure statistical correlation or pure symbolic logic, will neural symbolic computing unlock first? It might be discovering entirely new scientific knowledge, or finally achieving true, unbounded compositional generalization that we've been searching for since the beginning of AI research.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.